Okay, so we better put this thing down here. Today's tutorial. Okay. Yeah. And I think we've more or less covered it. Let's just have a quick look at the if statement. Quick look at the if statement. Very simple. If okay, let's just go straight to the flow chart. What we have is a evaluate condition. And then, if the condition is true, let me just put in a line there. White beans and the GCs there, okay? Keep the old voice there. If the condition is true, then you would have the code there that performs the do then stuff. And then you'd have a branch to exit. Okay, let me leave that there for a second. If the condition turned out to be false, you would have the do else stuff. And then continue. Okay, so after the do then stuff was over, you'd have a branch onto the next thing. Okay, so pretty straightforward templating approach. Okay, evaluate the condition before you do anything. If it's true, you do the then stuff and then skip over the do else stuff. If it's false, you do the else stuff and then continue. Okay, so that's one template. That's one template that you could use. Okay? So no doubt you'll come across those as time goes by. This is next week's practical, which you have out there in front of you. Just a quick look at it here. You've actually done it, most of it, but not all of it. Right? First of all, you've never written a subroutine. Okay, and we want you to write a subroutine to translate the sequence of ASCII characters that are meant to represent a signed decimal number into a signed binary. The second catch here is long word, not a word, but a long word. Okay? So you might have a sequence of characters. You might have a sequence of characters, something like this. Somewhere in memory, you might have a sequence of characters, like say, there might be a plus sign, or there might be a minus sign, or there might be a digit. Okay, you have to interpret it correctly. So you might have something like 9, 4, 1, 3, 6. And then some other character, like say a space character or a null character or something other than a digit character. Okay? And your task would be to actually turn that into whatever its binary long word, signed binary long word equivalent is. So you have to take note of a possible sign, and then you have to go and read these character by character and do the usual thing to convert it into a signed binary long word. Yes?
You're saying that the first character in the string is going to be a sign, or if it's a negative, it will be a minus sign, otherwise it would be.
It will follow our normal conventions. If there's no sign in front of it, it's positive. If there's a plus sign, it's positive. If there's a minus sign, it's negative. Your code has to distinguish between those three. The other thing to think about at any rate is what happens if somebody just puts in a plus sign, say followed by a space, and you're pointing to that. What would you do in a situation like that? I don't know what you do actually. To be realistic, it'd be good to flag some kind of an error, but but we're only learning how to write code, so perhaps we just ignore it and hope it will go away. Okay, but the problem is, the little problem with this is that you can't use the multiply instruction. Okay, you probably can't see that, but it's actually in your code. It's in your handout. The largest paragraph towards the end of the handout. One way to solve this problem requires multiplication by 10, but you don't have a long word multiply instruction, as you know to your cost at this stage, no doubt. So you could use your long multiplication routine, but actually there's a better way. So it'll be your job to find it. And I'm giving you a bit of a hint there, and I know at least one of you will have no trouble figuring out what to do. Okay, so that's next week's practical. It's worth 3%, it's worth more than this practical gone by or any of the other practicals, because there's quite a bit to do. You're writing a subroutine. I want it to be, I said, well behaved, and I haven't explained that yet. So you're writing a subroutine. It has to be well behaved, and you'll be using a main program to call the subroutine, and I want you to call it from a few places with a few sample character strings. Give space for a few sample results. So for example here, your main program might look something like this. Okay, it might look like org, say 10000, and all your main program will be doing will be actually calling giving values to it, giving appropriate values and calling the subroutine. So it'll be something like this. Move long, let's say S1 into A0. That's the value of the label S1, which will be pointing to a character string of digit characters into A0. And we'll be saying, let's say JSR2 get num, let's call it. Right, and then you'll be getting a result now. You're going to be designing the subroutine to a specification. You're being told what it does, of course, but you're also being told that the subroutine should be built so that it expects the address of the character string in question in A0. So that's part of the specification, and it's going to return the result in D0. Okay? So we take the result from D0, a long word, and we'll move it to R1, which we will define as well. So we might do that a few times. So we might just say 3 strings. And each time we'll call the subroutine, the same subroutine, but we're passing it different parameters, and we're dealing with the results in slightly different ways. JSR to get num. Move the result to R3. So we have 3 long words to find, R1, R2, and R3 is storage, and we have 3 sample streams to find. Okay, and then that'll be the end of it. Trap 0. Okay, so the main program will be called by the debugger, by your monitor, when you tell it go from location 1000, and program flow will come in here, it'll run through these effectively, and then it'll exit again. Back to the monitor. Okay? That's what the trap 0 instruction does at the end. Now, of course, we know, because we were now beginning to find out about subroutines, that what will really happen is program flow will come in here, alright, it'll hit that, it'll use that first instruction, it'll encounter this instruction, and program flow will go off to where get num is, which will be down here, we'll say. If we come in here, we'll have the code of get num, followed by RTS, return from subroutine, and program flow will return back to here. Okay. So program flow once again will come into your main program. It'll execute that instruction. The JSR instruction will transfer program flow to the subroutine. At the end of the subroutine, program flow will return to the next sequential instruction here. It'll continue on down, and it'll flow back out again to the same subroutine, and it'll return back now to the next sequential instruction from where the subroutine was called. And then we'll have, at this point, at JSR to get num, we'll have the same expression again. Program flow will go into get num, we'll go through all these statements, and RTS will bring it back to here, because pulling the return address that was stored by the JSR, pulling that off the stack each time. It's not a fixed return point, it's returning to where it's been called, just past where it's been called from. Okay, so that's the kind of flow you'd expect. So I would say you should put your main program first, followed by a trap zero. Don't forget the trap zero. If you leave the trap zero out, what would happen is program flow would go through all this, and then it would fall in, sort of tumble in to the subroutine's code without actually calling it a subroutine. And so we don't know what it will do down here when it will hit the RTS. Okay, well, just think about that for a minute. Maybe somebody could maybe guess what would happen. Okay, so we're imagining a pathology, something that's going wrong here. Okay, program flow, because we leave out the trap instruction here, it falls into the subroutine. What do you think is going to happen? Can anybody hazard a guess? Just imagine. Yes, sir.
It'll go back to wherever the last place is kind of marked as the return flow.
Well, kind of. Okay, I'll give you half marks for it. Yeah, it's not bad at all. Yeah. Why would it do that? Okay, let me ask you more. Why would it go back to?
Because the last spot is marked still in the memory, something like here.
Yeah.
Or wherever.
Yeah.
The last spot was back.
Yeah.
So
no, I see you just half marks.
It'll move outside the stack. You're like what's defined the stack, so they're just outside it.
Yeah.
So you'll try to go to whatever, you try to like execute the instruction of whatever code in that.
Yeah, you're more right than you. And it's interesting that let's just imagine you have the stack in memory. Okay, this is you're very close to memory. So you have the stack, and to take the points you made just up here, you don't actually know what is within the stack because none of your business. Okay, you've no way of telling, but there may well be something there. Okay, when the first, so we're at the very top here, org 1000, it's going to execute the first instruction, it's going to execute the second instruction, and in the course of executing that JSR instruction, it's going to push a return address onto the stack. So let's call that RA1, return address 1, which is this thing here. So it's going to do that, right? I think that's the kind of thing that you're thinking about. So while the subroutine here, getNum, is executing, the stack looks like this. Okay, there's a return address 1, there's a pointer to the next sequential instruction where the JSR was sitting on top of the stack. Okay? Now, where it departs from your idea is that when the RTS is executed at the end of getNum, it will take this return address and jump back to there. Okay, so that's okay, but it would also remove it from the stack by moving the stack pointer up to here. Okay, so the stack pointer is pointing to here. So while you're probably right that the return address won't actually be obliterated from the memory locations, it's no longer part of the stack structure. Okay, so it won't be found. Crucially, it won't be found. Now you notice that the JSR and the RTS are symmetrical in their use of the stack. One thing pushes on a long word, and the other pops exactly one long word off. So if you're looking at it quickly, they balance one another out. So you could say that the JSR to getNum will be balanced in respect of its use of the stack. So overall, the stack won't have been affected, even though it was made bigger temporarily and contracted again. Same with the second call to the subroutine, and the same with the third call to the subroutine. So come the trap, where trap 0, if trap 0 wasn't there, it would fall in, execute all the statements of the subroutine again, and then finally encounter an RTS. Now from our point of view, there's nothing in the stack to balance the RTS popping a long word out of it. So what it's going to do is it's going to pop something out of it, as you said. It's going to pop whatever happened to be there, the topmost 4 bytes, which could be anything. We have no control over them. And pop the topmost 4 bytes and jump to whatever location that appeared to represent. And bang, you've lost your program. It's dead. It's jumped off into hyperspace. It's jumped off a cliff into hyperspace, I think is probably a better way of putting it. Again, it's one of these security things. If you're trying to break into a program, perhaps you could trick around with the stack that doesn't belong to you, put the address of some sensitive piece of code in there, and execute an RTS, okay? And thereby jump off into perhaps an unauthorized part of the computer program, the computer memories, memory locations. Maybe start executing a sensitive program. Okay, so when you're very concerned about security, you have to make sure that kind of thing does not, or can't, not just doesn't. You can't say it mustn't do that. You want to make sure it can't happen, and usually you have to have recourse to hardware to do that. Okay, two very interesting responses to my question. But typically what will happen is it will just jump off into hyperspace, off a cliff into hyperspace, and it's over. It's gone. Okay, so you have a slightly, you'll be calling and returning from subroutines, and you have this complicating factor that I'm just adverting to here as well. Okay, but let's have a look at this week's practical. Let's just go back over this week's practical. Most everybody got a good go at this, and the marks that you got in the results, which are online, reflects that. Some of you didn't do so well, but most of you did very well. So let's go through it very quickly. And I only go through it quickly, but if you want to slow me down and stop me and ask me questions about it, because that's the idea, please do. Oh, sorry, just before I leave that, I didn't define. So I have the org1000, the main program, the trap 0 at the end of the main program, have the subroutines, any subroutines you might have. And then finally, the way I do it, I have, say, S1 and DC.B, say, plus, well, maybe that'd be the first one, so that'd probably be the simplest one, 614007. And maybe put in now 1, 2, 3, 4, 5, 6. Put in a space or a couple of spaces to make it even. 1, 2, 3, 4, 5, 6. It doesn't really matter. Put in some non-digit character to signify that we reach the end of the number, the sequence of numbers.
After we already had it before, that it was a string and then there's a comma and then a null.
If you want, you can certainly put in a string and a null to make it null terminated. It's up to you. You're going to have to effectively parse through this. So your code is going to have to be looking, if it's here, it's going to be looking at the next thing to see if it's a digit or not, right? And so on all the way through. So it suffices that it sees something other than a digit, whether it's a null or a blank or anything else, a dot, for example, it doesn't matter. Okay? So whatever suits you. So you have S1, S2, say DC.B, maybe one with a plus 9561493, and maybe if you wanted to put a null in for the hell of it, you know, it might not make a difference. And then maybe S3 DC.B, then a minus sign, say 21, something that we know and love. 21, let's say a dot after. Okay, so maybe 3 samples, and then you'd have R1 ds.l1 defining one long run of storage, but not giving it an initial value, or 2 or 3. ds.l 1. Okay, and then the end statement, right? So what I'm doing, as you might, of course I rubbed everything out, I have the main program, the subroutines, and the data areas. Now you don't have to do it that way. You could have, say, the main program and its data areas, each subroutine and its data areas, and general data areas. It's up to yourself. Just make sure that program execution doesn't fall into a data area, or doesn't fall through a program into a subroutine, or doesn't fall out of one subroutine into another network. You just got to make sure that isn't happen. Okay, so this week's, is that okay? I'm not sure I put it up there. Let's have a look then at this week's practice. Okay. Now, I want to warn you again that I've done this before, and so it may look very easy. I don't want to discourage you if you think it's not your anyone to do this kind of thing. Nobody's just writing it down. It's very difficult to get this stuff right the first time around, or only the first few times around. Okay, so we're going to write a complete program to translate a signed binary word integer to a null terminated sequence of ASCII characters. Okay, what I'm going to do, I gave you a hint about this, which I don't think many of you got. I said we did it before. We did. What we did in week 1 was we were using an algorithm to go from decimal representation to binary. Remember, repeated dividing by 2 and storing away the remainder? And you remember we noticed about that we got the digits in the wrong order. We got the least significant digit first. Well, here we're going to do exactly the same, except rather than go from decimal to binary, we're going from binary to decimal. Remember, everything here is in binary. So we're going to take the binary number, represented, stored in we'll say a register, and we're going to repeatedly divide it by 10. We're going to note away the remainder. So we take the remainder, we're going to store it somewhere. So what we could do that, and we could do that in the loop. And let's do that. Let's do that first. Complete program translate sign binary word. Okay, we also have to take note of the sign. We might use a register to store. Actually, no. Okay, we do it slightly differently. So let's imagine that we have the number in question, move.w, the num into, say, D0. So we're going to store it in D0 to be negative or positive. Right? We're just going to keep it there, and we're going to copy it into D1. Now I'm only I may make mistakes, so it's not impossible. D0 to D1. Now, we have to figure out whether it's negative or positive right now, because if it's negative, we have to get its 2's complement form so that we can get its magnitude and start repeatedly dividing its magnitude by 10. So, when you move something, if you look up the move instruction, the condition code register, I'm going to check this actually, the condition code register will be set according to whether the number is positive or negative. In other words, the end bit is affected. Okay? So I could say move a word from D0 to D1, and I could say branch if it's plus, branch if it's positive, branch if it's not negative. If you look at the condition code register bits to no flip. Okay, so I don't have to flip it. Yes, sir?
Are those numbers in X or what is that?
I'm sorry, which?
No,
oh, here.
The S1.
Those numbers are all, yeah, okay. That should be something else, 5 and say. Is that okay?
And how can this be sorted one by?
Each of these characters is stored in one byte because it's a character sequence. You see it's in single quotes here. Okay, so you're defining a character string here. Okay, so this is going to be 1, 2, 3, 4, 5, 6, 7 bytes long. Okay, so the code there. It's 7 bytes long. So you have that to be the character string, 1 character per byte. Okay? And the same with those 3. So the first one is quote 614507 space, okay, end quote. The second one is plus 9561493 end quote comma 0. In other words, a null terminated character string. Okay. And the third one here is minus 21 dot, minus 21 with the dot for termination. Okay, so to go back to our program, we're just checking to see if the number that we have is negative. If it's negative, we're going to flip it. If it's not negative, we're going to skip flipping it. Now, one of you asked me, how do you find out about all these tricks, like say that divide puts the remainder in the top half and the result in the bottom half, and so on. You have to actually go and look at the instruction set in detail. And if you download from online resources, you'll see there's 2 Motorola books there. Each of them, bedtime reading for you, a couple of pages on each instruction. Now, there's only 80 or so instructions, so they won't contain you long. But that's where you get the detail of what these instructions do. And there's an instruction called negate, okay, an instruction called negate, N-E-G, I think, and that will flip in the sense that we mean flip a negative number to its positive value. So I'm going to use it here. Negate the word that's in D1. Okay, so now I have in D0 the original number, which is still negative for this example, and I have its magnitude now in D1 no matter what. So we go on here to no flip. And this is a very common little construction here where you test to see if you need to do something, and if you don't, you just go on, you skip over the operation. If you do, you actually put that operation in there, right? So anyway, when we write this instruction here, we know we have the magnitude of the number. Now, I'm probably not thinking very clearly here, so I'm going to have to go back, because what I want to do now is repeatedly divide this number by 10. Now, the divide instruction takes the register that we're going to be dividing into, which will be D1, it takes it as a long word, and we have not done anything to the long word of D1, so we can't rely on the upper part of D1 at this point. So in order to get around that, I'm going to have to introduce another instruction here, move quick 0 into D1, just to 0 the upper half of D1. There's plenty of alternatives to this. For instance, here, right here, if I wanted, I could just simply do a sign extend or something like that of D1. So it's up to yourself. Okay? So I'm just going to put it in there. Okay, so now we definitely have in D1, we have a magnitude which we're going to repeatedly divide by 10. Sorry? Do I not have to add more to it? Oh no, so you were thinking of 2's complement is flip all the bits and add 1. Okay, so I'm going to change this. I'm going to change the name here, right? And then I'll come back to you. It's not negative. Okay, because I shouldn't have used the terminology flip. Okay, what I'm actually doing here is I'm getting its 2's complement. Okay, so I'm doing the full thing here. There is an instruction that will flip each bit in the sense that it's the union, and that is, I think it's called not, the instruction not, which just flips the bits. So flipping the bits is called a 1's complement, and negating is the 2's complement. Okay, so what I'm doing here is negating. Okay, so thanks for that. Okay, so let's get down to business here. We're going to repeatedly divide by 10. Oh yeah.
Why don't you take a note of the sign?
Why don't you take a note of the sign?
So if it's, you find it's negative or positive,
Yeah.
why don't you do it now instead of further on?
Why don't I do it now? Can you wait to be... Ask me that question in a minute or two. This is a good question. Okay? Okay, bear with me, right? Let's now go at this. We're going to have to rewrite this. This is wrong. Okay, divide one side. Okay, bear with me for a minute. Right, 10 into D1. Okay, let's imagine that the number was 48. So it's stored in binary. We have its magnitude in D1. We're after divided by 10. So we're going to get a result of 4 and a remainder of 8. The remainder is in the upper half of D1. So we're going to get a hold of it. So we're going to swap over the register. Okay, so we now have the 8 is in the word part of it, and the 4 is in the upper word part of it. So we have the 8. We want to turn that into its ASCII digit. So we're going to add the ASCII code of 30 to it. Sorry, we're going to add the ASCII code of the digit 0 to it, which is 30. Okay, so I'm adding that to D1. Okay, so 48 divided by 10, 4 with a remainder of 8. We've got hold of the 8. We've added the ASCII code of 0 to it. So what we would have in D1 now is, it'd look like this in hex. It'd look like 0004 in the top word and 0038 in the bottom word. Okay? So this is what we're after. We want to take this as the least significant digit, convert it to ASCII, and we have it. Okay, so the question is, what are we going to do with this? Okay, I'm being rude now. So we're going to have to think about this. So we move it off to somewhere. Okay, where? Okay, that's a question. But when we have moved it off and stored it wherever we're going to store it, we now are finished with it. So we could clear that byte in D1. So we've gotten rid of the 38. So we have 0004, 0000. Okay? We've gotten rid of the remainder and all its pumps. And we now can just swap this thing back over. Swap D1. So now we have the result. Okay? 48 divided by 10 has given us 4. And that's what we have in the register as treating it as a complete log line. So we're ready to loop around and divide that by 10 to get the next most significant digit, and so on. And it remains for us to decide when to stop, like banana. Okay? We have to know when to stop going back around this loop. And we could say this, we could say, if the actual value in D1, if the value in D1 is 0, we're finished. We're finished because there's nothing more to divide. There's nothing more to divide, so we will go back around here to actually not neg. As it happens, That's just a coincidence.
Shouldn't that check the input top? Because if I put in, say, if like the number is 4 or -1, you're going to divide it.
Okay, it's a very good example. The question, if I may paraphrase it slightly differently, is should we be doing this as a while loop or as a do while loop? Should we be doing it 0 or more times or 1 or more times? Now, I suggest to you that we have to do it at least once because we want at least one digit character to come out. The character 0. So we think that so if the number is 0, you want the character 0 to come out. So so I'm putting it to you that you have to do it at least once. You go around this loop at least once, always, no matter what.
You always have to divide.
That's right, yeah. You'd be wasted. You know, you'd be dividing, say the number is 4, as you suggest. You're dividing by 10, the result is 0, but the remainder is 4. So, you know, you're wasting a few instructions already. But it's not wrong. Okay, it turns out that if you look at the swap instruction, look at the instruction set summary, or look up debug, you find that you don't actually need this instruction because the swap instruction sets the condition code register on the result of, he keeps doing this to me every Thursday, the swap instruction sets the condition code register according to the result, according to the state of the register after the swap has occurred. So if the register is 0, the Z bit will be set and it will drop through the DME. Okay, so it will drop out of there having done all the digits, no leading zeros, unless the value of the number happens to be 0 to begin with. Yes, sir. Just a second till I try and quiet this thing. Yes?
Why did we swap the people and why did we move to 0?
Yeah, well so why did we go to the trouble of bringing it into D0 and bringing it over to D1 and all that kind of stuff? That's your question.
Why did we swap D1?
Here.
Not there.
Here. Okay, why did we swap D1 here? Well, if you take an example, right, the example we were using was 48. When you divide 48 by 10, the result you'll get in D1 here is you'll get the result 4 in the bottom word and you get 8 in the top word. Okay? That's the remainder, and this is the result. And it's the remainder we want to process at this time. So we need to get that over into the right-hand half. But we don't want to lose this 4 because we're going to use it later. So we use the swap instruction to get this configuration. Because that's what the swap instruction does. Okay? So just to get hold of this, so we process this here and here, right? And then we clear out D1, we clear this back down to 0 down here, and we swap them back over again. Okay? So at this point here, what we have is 0, 0, 0, 0, 0, 0, 0, 0, 4. Okay, so we had to swap basically to get at the remainder. And then we swap it back. Okay, now, I thought you were asking another question which is related to the question that was put to me here, which was, why didn't I take note somehow of the fact that the number might be negative up here?
Because you're working backwards.
Well, I'm working backwards, yeah, but I still have to take note of it. Okay, so yeah, it still doesn't know what the answer is. Okay, there's two big problems here. And one of them is that I have allowed for the fact that the number might be negative, but I haven't remembered, or at least it doesn't appear as if I've remembered, whether the number was negative so that I could put out a minus sign in front of it. That's one problem. Okay? The other problem, though, is, what is the other problem? Somebody's going to tell me what the other problem is. This is where a lot of you did this and got it working pretty well, and then ran ashore, my mother would have said, because you know what was going on. Ran aground. So what would you do? What's the problem with this thing? Anybody tell me what the problem with this is? The wrong way around, yeah. It's backwards. So we're getting the 8 out first, and we're going to get the 4 out next. So how do you deal with that? You could say, like Microsoft, you could say, well, that's just the way it is. You know, you get the result. It happens to be backwards, but you know, what about it? What's the problem? What's your complaint? See, you could have could have done this, right? ds.b. First of all, let's figure out what the longest character string could be. It could have a signed character, that's 1 byte. It could have 32768, that's 5-digit characters, that's 6. And null to terminated, that's, what's that again? 7. So let's keep it even and say we're going to reserve 8 bytes to store the characters. And let's say, okay, up here we'll initialize things. We'll say we'll move the long word whose value is the value of the label string into A0. So in other words, A0 is pointing to where we're going to put the result, right? And then down here you could say, I'm going to take the character that I've just generated, I'm going to put it out where A0 is pointing and post increment. So you could do that, but you'd be getting the thing backwards. And as I say, Microsoft is very happy with that as a first pass anyway. That'll be version 1. They usually get as far as about version 4 before they get anything that's good. But that's, and they make lots of money. Okay, so what other ways could we have to solve this problem? Okay, tens of thousands. Yeah, there is another completely different way of going about this, and it is to find out how many units of 10,000 are in it. And that you could certainly, if you had a computer that didn't have a multiply instruction, for example, you could subtract 10,000 as many times as possible, and just count the number of subtractions that were successful and use that. And you'd be starting at the most significant end and working downwards. You certainly could do that. Any other ways of doing it? That would work. Yeah. Any other ways of doing it? Okay, so you could take the I've been a bit hard in Microsoft here. You could actually say I go up to the upper end of the string, okay? Say string plus 7 into say A0. Okay, so A0 would be pointing to the top end of the string, and you could work downwards. So you could say you could pre-decrement.
Size of the loop operation.
Sorry, do you need us to be here for this?
Does the size of the loop operation not change? Is that 7 is on the 7 onwards? You're adding 7 onwards.
Okay, so here, the value of this expression here is going to be calculated by the assembler to be equal to the value of the label plus 7. So it doesn't take any account of this size here. Okay? The size of the pre-decrement is 1 because it's byte size. So we're in the clear there. Well, what's wrong with this? Is there anything particularly wrong with this?
The number's shorter than 5.
Yeah.
Yeah.
The problem is that unlike the opposite of the problem we have with banana, it's not that we don't know where to end it, so we don't know where to start when the thing has been finished. Because if you think of having the 8 characters that you have available, you have, say, the character 8 and the character 4 in our example, and you have all these empty spaces. Well, it wouldn't be empty, they'd be full of whatever junk happens to be there. Okay? So it's not being lined up with the start of the space in which the answer is supposed to be placed. That's what I think is wrong with it. Now, by the way, there's no null after it, that's very easy to fix. Okay? So what you could do is you could say, okay, I'll copy them all in here, and actually this might work. I'll copy them all in here as I've indicated, and when I'm finished, I'll move everything up to the start of the memory, of the allocation space. So I'll move this 4 up to there, this 8 up to here, and the null up to there, and that would be completely okay. Yes, sir? This is pre-decrement. This is address register in the pre-decrement. The pre-decrements first and then moves.
Is this the right syntax? Because I think I tried it yesterday and it didn't work.
Yeah, this is the right syntax of it. Yeah. We'll check your code later. Okay, so as far as I know, the syntax is right. Although the chalk does play hell with the typewriter at home. So it just seems to me that we have a little bit of an issue. So I'll tell you the way I would solve this problem. I would use the stack. Okay, I want to use the stack. Actually, I'm itching to use the stack. And so I do ever so slightly differently here. Okay, first I might just use a bit of chalk here. Okay, so the first thing I would do is I would, you see the stack is always there. The stack has to be working because subroutines and so on, the system uses the stack. So we can assume it's there, and we can assume that we can use it for holding relatively small things, like say 8 bytes or even maybe a couple of hundred or a couple of thousand bytes would be okay. We can assume that it's there and has space to grow to allow us to do that. So I'm going to use it. Now what I'm going to say here is, initially, I'm going to put a marker into it. I'm going to put the null character in as a marker. So I'm going to say here, move a byte whose value is 0, that's the null character, onto the stack. Pre-decrement A7. A7, remember, is the stack pointer. So that's my null character, right? And each time I discover a character, I'm not going to put it in there, I'm going to put it onto the stack. Okay? So as the character, as I discover the character, I'm going to push it into the stack. Yes?
Every time you consider A7, it's just flash it to the stack.
Every time you use A7 pre-decrement, yes, yeah, it's being pushed into the stack here. Because A7, you're not supposed to use A7 for anything other than the stack pointer. Right? So you can always assume, therefore, that it is pointing to the stack. Yes, sir?
Is there any difference between declaring some memory space, preserving, and then each of the same way you use it?
Is there any difference between reserving part of memory to use as a stack effectively and using A7?
Well, using A6 and start.
Okay, just to be clear on this, you certainly can reserve memory space and you can use it as a stack, but you should not use A7 to point to it if you use some other register. That's what you're asking. It's not quite the same thing, but it's almost. I mean, it's virtually. So let me just come back in a minute and explain there's a very slight difference. Okay, so we're pushing the characters into the stack. They're being generated backwards, but they're being pushed into the stack effectively backwards, and we can take them out the right way around. Okay, so at the end here, okay, now if you're taking this down, you have to leave a little bit of space because there's something else that has to go in there. At the end here, I'd be saying something like this: move along the value of the, what did I call it? Result, was it? String? So I want to put the result into A0. So now A0 is pointing to the location I want the first character of the result to be placed, and all the characters are in the stack. So all I need to do now is move a byte from where from where A7 is pointing, and post increment. So I'm going to pop it out of the stack into where A0 is pointing. Okay? And if the character is not the null, because I put a null in there as a sentinel or as a marker, I just loop to reverse. Now I don't need a compare instruction because the move instruction sets the conditional register according to the item that's just been moved. If it's the null that's been moved, the Z value will be set and it will drop out, having transferred the null. So we get the null terminated string in exactly the right place, in exactly the alignment that we're after. Okay, but there's still a problem. Well, still a bit of a problem. Yes, sir?
What's the story of moving from one register to another in the same state? Is there any problem that's not like?
What's
I had a problem with that, moving from one register to another at the same time. It's really easy to read it from the first register.
I don't know that problem. I have to see the code, honestly. Yeah, must have been something else. It was probably the way they were holding them out or something. One of those kind of little things. Okay, so the other problem with this is the sign. Okay. I was challenged, I think is probably a fair statement, as to why I wasn't remembering somehow the fact that the number might be negative.
I said, why didn't you do it up there?
Why did I do it up there? Yeah. Well, it's the same difference. Yeah. And the answer is that well, you might be right, by the way, but the way that you'd remember it would be such that you decide around here that you needed a minus sign in front of that string of digit characters, no?
In like a year prior. I did it as the very first thing in the program was positive.
Yeah.
Then you print your space of course and it's negative. And then I did the rest of that.
Oh. Well, I wouldn't have done that. But you might be, I mean, joking aside, I don't mean to pick it up. You might be right. Unlikely. So, the thing is that we actually have the number itself in D0, and it can be used as a flag to indicate whether the number was negative or not. So here, I can simply do this, test the word that's in D0. If it's positive, I'll just, what do I call it there? No sign. I don't need to put out a sign, right? If it's negative, I could move a byte whose value is the ASCII code of the minus sign onto the stack. And then I have no sign here. So that's the way I would have done it, right? I mean, in other words, D0 was my way of remembering that the number was negative. Okay? And your way really might be just as good at it.
Does it not require one less instruction to do it at all?
Does it not require one less instruction? Well,
you don't have to do the test instruction to do it at all.
That's right, but you don't have a place to put the minus sign because the minus sign goes in front of the...
You do, because you can put the move.l, the value between A0 to the top, and then increment A0.
Yes, indeed, yeah, you could, yeah. So if I put this instruction here, move the value of the first location in the string space into A0, I could at the start, and is that what you were getting at as well? I could work out that it was a negative number, put the sign in, and leave A0 pointing to the next free space. Yes, indeed, sorry, I didn't get that. Yeah, so that would be better. There would be one instruction short, and actually be slightly better as well for reasons which I don't go into just now. Okay, so that was the way of doing it. Well done to everybody who got it working, and well done to you guys for persistent by telling me that I was wrong and being correct. Thank you very much, and we'll see you next Monday.